I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where this question has been posed and it will be answered. For an object that is in free fall, does the force on the object change during its descent? At any time period where the object is in actual free fall, is the force on that object changing? You need a function to start this off, and for some of you the answer is obvious from the start, and for others the answer is not so obvious. But let's proceed. The object will have a time which would be a reasonable time from the start of the experiment to some finite value, and we can even come up with 10 seconds even though we won't use it, but I'm just telling you the experiment would involve a time from 0 up to a reasonable time where it takes for the object to hit the ground. It could be 10, it could be 20, 100, who knows what. It certainly would not be infinity. Anyhow, position of the object for an object in free fall can be given by this equation, half a t squared, where a can be replaced with g, your gravity, but we're keeping everything in terms of s, a, and v, position, acceleration, and velocity. This here is your function which starts everything off. If you look at this function, you know acceleration is constant. You have two constants and you can write it like this, a over 2 t squared, because the variable which is present here is your time. As the object is dropping from a certain height at a given time period, the velocity will change, the position will change, because if this right here represents the initial position and where you measure it, that would be the final position, and then the difference of the two would be your delta s. But likewise, you'll also have a delta t from your time 0 to whatever time you're measuring it. You have a change in time, you have a change in position. You'll also certainly have a change in velocity. But let's proceed. So we have this as our function, a over 2 t squared. So if you were to graph this a over 2 t squared, you know it would be a parabolic graph starting here from the origin, because we're looking at from 0 and then going up like this. This is my position function and it looks something like this. Here's 10 and here's 0. So when you want to determine the slope of this, why do we want to determine the slope of this? Because velocity is always equal to change in position over change in time. If you were to do a slope determination, pick any 2 points. Here's one time right here, we'll call it time 2. Here's another time t1, and you draw a secant line between the two and you determine the slope of the secant line. You'll get an average rate of change, but as you change this time, your second time, and you bring it closer and closer to your original time, you can convert that secant line into a tangent line, which is the essence of a derivative, and you can present it like this. Limit as this t, the delta t is approaching 0, the difference between the two times where you're doing this average slope determination, as it decreases, your this delta s or delta t, your slope will approach that of an instantaneous rate of change for a velocity, and it'll give you what will be the velocity function, and that right there you can easily do by means of derivative. I'm not showing you the lengthy procedure, I'm just doing the derivative. The derivative of something like this is easy. Your template is x to the power of n. When you do a derivative, this becomes a coefficient and this is reduced by 1. I have a over 2 t squared. This right here is my constant, this right here is my variable. The 2 will come over here and it'll be reduced by 1. So I'll have a over 2 times t to the power of 1. When you simplify it, you'll have a at. And that right here will be my velocity function at. But look, you have here a parabolic function and now you've ended up with a linear function at. It's a linear function. Once the derivative is done, we've arrived here at the velocity function. Remember, we're still answering this question for you, but we're not skipping out on any steps here. We have determined by means of a derivative the velocity function is equal to at, and you know it's going to be a linear function, and it would be looking something like this, and we'll terminate over here. Here's 0, here's 10. Now if you were to do a derivative of this, you pick 1 point here, 1 point here, you can do your slope. You can easily do a change in y divided by change in x. Here you know the time is along the x, here you know velocity is along the y. Your slope over here will be change in velocity divided by change in time. What's change in velocity or change in time? It's the definition of acceleration. When you do the derivative of a velocity function, you will get an acceleration function. And what will the derivative of a t be? You know here a again is the constant. You're doing the derivative of t to the 1. You bring the 1 over here, you reduce it by 1. You have a times 1 times t to the power of 0, which is just equal to an a. So this gives you your acceleration function, which is equal to a. So now let's bring out the acceleration function. We have started here from a parabolic function, which is your position function, to a linear function, which is your velocity function, to what will be another linear function, but will be horizontal line. Your acceleration with respect to time is equal to a. If you were to graph it out, it would be just like this, from 0 to 10. But do you know what the slope of a horizontal line is? It's always equal to a 0. Why? Because there's no change in y, there's a change in x, but you don't have a change in y. Where here you have a 0 over change in x, so it's always equal to 0. So there is no change occurring here with regards to acceleration. What does that confirm for you? That acceleration is constant over the entire time period, 0 to 10 seconds, or whatever that would have been. If you do the derivative of this, you know you're going to get a 0. Why? Because you're really looking at a times t to the power of 0. Again, the variable in all of these cases is our t. You bring it over here and you reduce it by 1. You'll have a times 0 times t to the power of minus 1, which will be equal to a times 0 over t, which is equal to 0 nonetheless. So we're getting here the derivative of this is equal to 0. When I do the derivative of my acceleration function, which is a horizontal line, I already know it has a slope of 0, but by means of the derivative procedure, I confirm it to be 0. So let's look here at our question. For an object which is in free fall, does a force on an object change during its descent? You know force is equal to mass times acceleration. From these three items, force, mass, acceleration, this here is a scalar quantity. Force and acceleration are vector quantities. But if the mass is going to stay constant for an object, the only way the force can change is the acceleration must change. But if the acceleration is going to remain constant during the entire time period that the object is dropping, the force cannot change. So the answer to this question is no, the force will never change while the object is in descent, because if you look here at the acceleration function, your time variable has vanished. The acceleration is no longer dependent on time, because whatever the time might be while the object is dropping, the acceleration will remain constant and it will be a, your 9.8 meters per second square. Horizontal line indicates that there's a slope of 0. A slope of 0 means that one variable is not changing with respect to another. Acceleration is not changing at all during this time period. Therefore, with acceleration not changing, the force must not change. The force will remain constant for the entire period that the object is in descent. The minute it hits the ground, something will change, the acceleration will change, and then the force will change. But during its descent, the force will not change. And that right there brings us to the end of this video. Thank you for watching.